So, mixed strategies play a critical role in game theory. In this game, in this predator-prey game, there is only a mixed strategy in Nash equilibrium. So the question is, the first question to ask is, what do these mixed strategies really represent? Are there insects there having some randomizing devices in their tiny little brains that are determining their actions? This turns out to be a quite a deep question, and there are multiple ways to look at mixed strategies. Here are three. The first is indeed to think about facing a player who is randomizing, and we have ample examples. When the Internal Revenue Service decides who to audit, they definitely are randomizing. Or when in the airport the security personnel decide which people to pull aside and conduct a more detailed check on, again, they are using various randomization techniques. But a very different perspective is thinking of the mixed strategy as not something that's happening in the head of that other player, but reflecting your uncertainty about their behavior. So they are really behaving in a very deterministic way, but you have some assessment of how that deterministic way is. So, for example, a firm, a competitor of yours, you may be, say, a cell phone manufacturer who is deciding whether to enter a market, and there's another player out there who are going through their own decisions, and you may have an assessment, and of course whether they enter or exit the market will have strong impact on whether entering a market for you is beneficial. And you may have some assessment about their decision-making process and end up with some assessment that with some probability they will, say, enter the market. So that would be another way to interpret the uncertainty, the mixed strategy of the other player. Another famous example, quite relevant in the last decade or two, but in fact was a very salient in the mid-50s of the 20th century when game theory was given a major push, was reasoning about international conflicts, whether it's weapons of mass destruction, nuclear weapons, or what have you. You have one party who is deciding whether or not to construct weapons, say, in contradiction of a treaty, and another party who can inspect the activities of the other party, although doing it rather not exhaustively, so they have to have some strategy about how to do it. And you, if you're the party who are deciding whether or not to create weapons, might have some assessment of the probability that they would inspect it in a given location. There's a completely different way of thinking about it, where the agents involved are really not doing much reasoning at all. In fact, they may be insects. But you might be facing many different kinds of insects. And the mixture is really the probability of encountering an insect or a player of a certain type. So you have a mixture of populations, and the mixed strategy reflects the relative components of a particular population in the mixture. These are all different ways of thinking about the mixed strategies and mixed strategy equilibria, but they really don't impact, for the most part, how we apply the theory. Another point to make about mixed strategies is the following. So we saw games that had pure strategy Nash equilibria. For example, Prisoner's Dilemma has a unique equilibrium. We also just saw a game in which there was no pure strategy Nash equilibrium, but there was a mixed one. But as you might guess, there are definitely games that have both. And here is a game, and we've seen this game before. This is Battle of the Sexes. So I and my significant other want to go to movies. We have opposite preferences. I would like to go to one movie over the other, and She has the opposite preference. But above all, we'd like to go together. So if she decides to go to one movie, I definitely want to go to the same one. I would prefer that it be the kind of movie I like and not the kind of movie she likes. And the same goes for her. And here is the payoff matrix corresponding to that situation. Now, we immediately see that we have two pure strategy natural equilibria. Again, if she decides to go to one movie, say this one, then I definitely want to follow suit and go to the same one, and conversely here, and the same goes for her. But is there also a mixed strategy natural equilibrium? Well, let's take a look. We go through the same reasoning as we did before. We say, let's assume that we are both mixing both strategies of ours with some finite non-zero probability. So let's think about it first from the row player's point of view. If the column player is mixing, let's call their mixture probabilities P and 1 minus P. Now, if I, the row player, am randomizing, I'd better be indifferent among playing the two strategies, namely playing this one and this one. Well, what's my payoff when I play this one? It is P times 3 plus 1 minus P times 0, which is written right here. This is one expression. Similarly, my payoff for playing P is this expression right here. And if I'm indifferent among them, they better be equal. And when you do the simple calculation, you get that P is equal to 1/4. So this is all from the row player's point of view. Now let's think about it from the column player point of view, and we'll go through the very same calculation. And whereas from the for the row player, they would put a weight of 1/4 on the left strategy, we'll see that the column player will put a weight of 3/4 on that, and we'll get the simple equilibrium of 1/4 and 3/4 on the for the two players. So yes, we saw in this game two pure strategies and one mixed strategy. And we can start asking questions. And that takes us to the realm of complexity of reasoning about games, which is an area that has been very active. We won't go into much detail into it right here, but let me give you a taste for it. So first we could ask about this very same game, Battle of the Sexes. Might there be other equilibria? Well, the answer is no, and we can simply inspect it and look at all combinations and see that these are all the possibilities. But more generally, if I give you any game, if I give you some set of equilibria, each equilibrium can be checked to see that indeed it's an equilibrium. But how do we know we found all of them? And the answer in general, we don't. We need to look at exhaustively at all combinations. You might ask what might seem even a simpler question. Okay, I just want one natural equilibrium. How hard is that if I go beyond two by two games? And the answer is very interesting and deep, and the short version of it is it's hard. Computer scientists like to think about in terms of complexity classes, a whole class of problems, and looking at the set of problems that are hardest for that class. It turns out that there's a class that's been dubbed PPAD, for which finding a sample natural equilibrium is the hardest problem in that class. So it's a hard problem, and what do you do about it? So in general, there are two types of answers. One is we find solutions are good enough. We look for algorithms that work well in practice, in situations of interest. The alternative is to restrict the space of problems rather than look at all possible games, look at a smaller set. We already saw that in 2 by 2 games, the situation is simple. Well, maybe there are situations that are not as constrained as that, but still give rise to tractable algorithms. And as I said, that's a big area of interest, which we won't at this point get into in detail.